Hey, the last thing that we had is so the last thing that I went through some things through when we were last together last week was that if you have some integral domain and you've got some proper ideal, then there exists a valuation overlay. And let me remind you that, of course, what I mean by that is that is some ring between R and its quotient field, such that I survives in V. And that is to say that when you lift I up to this valuation over ring, it's still a proper ideal. It doesn't blow up because it becomes a whole ring. And this is sort of, I think, the last piece of the puzzle that we needed for this truly wonderful theorem. So here it is. Here R is an integral domain with quotient field K. So we've talked about integral closure, right? What is the integral closure? I'll call this R bar. And just for a quick reminder, this is all the stuff in K, such that omega is the root of a monic polynomial. And right, so it's all the stuff in the quotient field that is the root of some monic polynomial. Then here's the big result. The integral closure of any domain is the intersection of all the valuation rings that contain it. Right? This is a really cool result. Right? So all you have to do is take every valuation ring that contains R, intersect them, and you'll get R bar. Here's a nice corollary. So here's a couple of corollaries, something that follows consequences from this. Corollary one, R bar is ring, right? Because this was something we went through some pains to show earlier, wasn't it? Right? We had to show that we did the module theoretic characterization of what it meant to be integral and said, oh, look, these are both binary generated modules, blah, blah, blah. Well, now it's immediate, if you believe this theorem, because any intersection of a bunch of domains is certainly another domain, right? How about that? Right. So that's kind of groovy right there. Corollary two. R bar is integrally closed. So this is in fact a closure operation, right? Because what happens when you take the integral closure of R bar right? My claim is that you get R bar back. Well, now what you do is you intersect all the valuation domains that contain R bar, but all these did in the first place, and therefore the integral closure is back where you start. So the integral closure is integral closed. So that's a couple of really nice, quick rip-off theorems that probably aren't obvious that follow immediately. Right? So, big gun, why is it true? Um, note. Okay, so somebody can explain why this is true. There's a couple of things that we know. Number one is, what do we know about valuation domains? They're integrally closed. Uh, each V is integrally closed, right? That's one piece we know. And two, if VI is a collection of integrally closed domains, then the intersection of VI is integrally closed. Right. So everything that's integral over R, right, is integral over V. So each R bar is contained in each of these V's, and these intersection of V's are closed. Right, okay with this? The interesting part is, of course, why is the intersection of evaluate? Why is it integral closed? Right. So we aim to show now that the intersection of V is contained. Okay, so here's the fun part. Assume X is in V for all valuation operands of R. Somehow I want to come to the conclusion that X is in fact an element that is integral over R. Now, I don't want to be writing a bunch of polynomial equations here, so let me recall this. X is integral over R if and only if, get this right. Anybody remember? Anticipate what I'm going to write next.
Either X or X inverse is in R.
You're on the right track. Or am I going to write?
I already like took notes over this, so I feel like I'm cheating.
Go ahead.
It can only if X is in R or it can only X inverse.
Right. Y'all remember this business here? Okay. So, so this is what we wanna show. So let's suppose we wanna show that X is integral, so it suffices to show that X is in our X inverse. Suppose well, what this means is of course, this ring contains all of R and it contains the element X inverse as well. Now, X doesn't live there, right? So that means that X inverse is a non-unit, right? Or X inverse. Because X isn't there to invert it. So the ideal here is proper. And what do we have from our toolkit? Well, we have that if you have a proper ideal, then there's valuation overing where this survives. So there exists a valuation overing. Say W containing Rx inverse, which of course contains R, such that X inverse survives, or X inverse W is strictly contained in W. Therefore, X is not in W, which is a contradiction, because X is supposed to be in every valuation over R. So end game. So X is integral over R. And so we get this containment and hence equality. Any questions on that? This is a really, really cool theorem because it gives very, I mean, it's not really clear, is it? It's the intersection of valuation rings, it'd be a bunch of things that are roots of polynomials, but that's exactly what happens. Let me give you another corollary, just kind of fun. Let me point out here that I'm just doing this for fun in the following sense. We've already shown that in fact any UFD is integrally closed. So if any UFD is integrally closed, it's certainly any PID is. But here's kind of a way to see this. Well, let me be complete here. Proof. This is certainly true if R is a field. So in the special PID case that R is a field, any field is integrally closed, no problem though. So let's assume that R is not a field. Well, what happens with fields? Then you have non-zero prime elements. So let P be a non-zero prime element of our PID. What can you say about the ideal generated by P? Y'all find it a little more machine here?
Yeah.
Yeah, it's kind of torture. Yeah. You must be.
There's that subjectivity.
Notice that P is of course a prime ideal, but since this is PID, what else can we say? It's a non-zero prime ideal, so it must be
Maximum.
maximum, right, as well. So. And notice our localized P is a. What's that?
Field.
No, because the ideal P will survive. It is a valuation domain. Because this one's actually a principal ideal domain, localization of principal ideal domain, still is a principal ideal domain. And this has only got one prime. So if you take any two non-units and compare them, they will be up to a unit P to the A and P to the B. One of those divides the other. Right? And so integrally closed. And so notice that R is the intersection this is a general result we proved earlier that if you have R is the intersection of R localized and M for all maximal ideals, which in this case is the intersection of RP. Which is integrally closed. Because these are all valuation domains, so R is equal to this here. So as a corollary, if the PID is integrally closed. Yet another. Okay, any questions on that? This is a useful result that I don't think I've proved to you all. I'm going to give this characterization. I think I've sort of hinted at it, that this is a characterization evaluation domain. I want to prove this for you. And then we're actually going to talk about valuations as I promised earlier. B is a valuation. If and only if B is a quasi-local bunch of European marks on that. Anyway, so B is valuation domain if and only if B is both quasi-local, so it's got a unique maximal ideal, and Bezout. So I think that I said when we first started talking about valuation domains that in my list of properties of valuation domains, when we started, we pointed out at some point that valuation domains have to be quasi-local. They're because all ideals are comparable, so there can only be one maximal ideal. Given two maximal ideals, one of them contains the other, right? So there's only one. And we also point out that it was Bezout, which means that any finitely generated ideal is principal, right? We did this kind of by induction. So we've done this. Kind of cover this ground here. The question is, why do these two conditions give you what you want. So, I'm going to assume that I've got a quasi-local Bezout domain. I'm going to show its valuation. So let's let pick two non-zero elements of V. I want to show that one of them divides the other. So to this end, I want to show one of them divides the other. So let's look at the ideal generator matrix. So let's consider the ideal generator matrix. Now, I don't know much, but I do know that V is Bezout. So this thing can be generated by a single element. Maybe not one of those, but I'm going to call it something. X. So this two generated ideal can be generated by one element, X. So we'll say that X divides A and X divides B, right? That has to be the case because X generates its ideal, so it's got to pick up both these generators. And so if convenient, I'll write B equals B prime X and A equals A prime X. Okay. So where might we go from here?
Know that either B prime or A prime is a unit.
Right. So I've done sort of halvesies on this, right? Since the ideal generated by AB is singly generated, it's certainly true that X divides these. But what does the other containment tell me?
Right, the winner.
That is correct. The other containment works too, so that means that X is in here somewhere. So it's a linear combination of A and B. So there exists R and S, and what did I call it? I called it B. R and S and B such that R A plus S B is equal to X. Okay, well, I can improve this because this is R A prime X plus S B prime X is equal to X, right? And of course, I'm living in a domain, so I can cancel out the X because clearly, since A and B are not zero, X can't be zero. So I get R A prime plus S B prime is equal to 1. Right. Now, my question is, how does that help?
At least one of, you know that A prime and B prime can't both be in your maximal ideal.
Note. B is quasi-local with maximal ideal. Let's call it something. M. Right. So now I'm throwing the quasi-local at it. If A prime and B prime are both in M, then R A prime plus S B prime cannot equal 1, right? Because this side of the equation here would live in the maximal ideal here. This would live in M, and that's a contradiction. So at least one of them is not in the maximal ideal. So without loss of generality, we will say A prime is not an M. And what, pray tell, does that mean about the status of A prime? Because of the fact this is quasi-local, if it doesn't live in the maximal ideal, it has to be a unit, right? state it this way. So A prime lives in no maximal ideal. There's only one to live in, and it doesn't live in it, right? And what kind of element lives in no maximal ideal? Only units. So A prime must be a unit. Okay, so I've now got this thing token on the run. So let's go back to what everything is. So A so A prime, because this thing right here is a unit. So A and X are essentially the same. They're just unit multiples of one another. Since X divides B, then A divides B. And so B is the valuation. Any questions? All right. Okay, so any questions? I really think this through. Now, you may wonder where this terminology valuation may come from. I mean, valuation, that sounds like, you're at Kroger's putting prices on stuff, right? I mean, it sounds like you're assigning a number or something to it. And what does this have to do with, given two non-zero elements, one of them divides the other? Well, so let me tell you, I'm not having a stroke here. This is actually part of the plan, and I'll tie this together. So what is a valuation? Let me give you the following definition. What A, B, A, you could like a valuation on K is a function V from I want to do this on the non-zero elements K into I don't know why it's V here into G where G is a totally ordered abelian group. And what I mean is an abelian group, which I hope we're all comfortable with, and a total ordering is just, there's a way you can compare elements on it that such that given any pair of elements in the group, they're comparable, right? A is less than or equal to B, or B is less than or equal to A. For a totally ordered abelian group, you might think the integers, right? Given any two integers, one of them smaller, less than or equal to the other one. The rational numbers, the real numbers, well, let's not make it complex because that doesn't work out too well. But any totally ordered abelian group that you desire, satisfying vault A, B, and non-zero elements K. I want the value. Sometimes the output of this function is called a value. The value of the product of two elements is the sum of the values. So in this sense, it behaves like a logarithm, right? That's kind of what it's meant. And two, I want something that helps deal with the compatibility or the additivity. B of A plus B is greater than or equal to the min of the value of A, value of B. And this is of course provided A plus B is not equal to 0. Because if that were the case, the value, the function would be undefined. Some people, define the value of, let's see. Let's see what happens. Anything about the word. Yeah, some people define the value of 0 to be infinity, to get around this not zero thing, right? But so I would have had to recouch it, totally ordered billion group plus infinity and, value of 0 is a bit. Let me give you some examples here. But well, actually, K. Quotient field. Like either would be the quotient field of F power X. By the way, let me point out that K is equal to, in this case, all you have to do is stick on 1 over X and that inverts everything in here, right? Because in F power X, you've either got 0 or you've got X to the n times a unit, right? So when you throw in 1 over X, that inverts everything. Well, except for 0, right? Okay. By the way, what do you suppose there are? Well, what's the most economical totally ordered billion group that you can think of that I could use here?
And C.
Agreed. Okay, let me tell you how the math's gonna work. If A is in K, but is not 0, then A can be written in the form X to the N times U, where N is in the integers, and U is in units of F power X. Because any non-zero element of the quotient field of this can be written as X to the A, U1, over X to the B, U2. Right? As long as it's not 0, I don't want a 0 on the top or the bottom. And this is X to the A minus B, U1, U2 inverse. This is still in the units of F power X because I can invert U2. And this is a general power of X that could be positive or negative, right? So anything in here is written this way. So B of A equals B. This is another one of my great examples of, if you're doing math, it should be easy. What's the best way to get an output in the integers? N, right? Notice that, of course, B of X to the N, U1, X to the M, U2, is equal to B of x to the n plus m, u1, u2, and this is still a form power of x times unit in there, which is n plus m, which is v of x to the nu plus the x to the m, well, u1, u2. And what happens with this min business? Let me see if I can kind of wrap my head around this. What happens when you do this? Without loss of generality, we say n is less than or equal to m. Right? Because again, totally ordered, so one of these is less than or equal to the other one, right? Well, how does this help? Well, in this case, we have v let's see, one. Now, oops, what does this turn out to be? Well, this is a power of x times something, right? But how do I move forward from here?
That bit of it on that side of the unit, because U1 has a unit constant term, and so the entire sum is constant.
One thing you might be overlooking. What happens if m and n are equal, right? And this is x is 0. But let's record your observation first. This is equal to n if n is strictly less than m, right? Because what do we have in this case? In this case, u1 plus x to the m minus n u2 is a unit. And right, because this begins with a unit term, and here you've got some power of x times something else. It doesn't interfere with the constant term, still a unit. So this becomes n in this case, right? Okay. What happens if n equals m? Well, in this case, this is just u1 plus u2. So you might get lucky and add these up, and u1 plus u2 is still a unit. That's certainly possible, right? I mean, depends on the field, doesn't it? It's like if you take the power series and q power x, 1 plus x plus x squared plus x cubed, whatever, and then you take 2 plus x plus x squared plus x cubed, etc. You add those two power series up, they're both units, you get 3 plus 2x plus 2x squared, blah, 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 still a unit, right? But what if you add 1 plus x squared plus x cubed to negative 1 plus x plus x, right? Then all of a sudden, this can induce a higher power of x, right? When you add these up, then what could happen is you get a higher power of x. And I will assume you don't get 0, right? They don't completely cancel out, because I'm going to go under this assumption here that what I added up is not 0. But everybody see what happens? If u1 and u2 are the same, it's possible that it strips off the first component, making this whole thing a big fat power of x. So now you've got a bigger power of x comes out there. So this is at least n. At least n, right? So this is greater than or equal to the min. let's look at another couple of examples. I'm gonna come back to one that's similar to this, but. Example. Okay. Okay, what's valuations on that?
Got the usual one. Valuation is itself.
Oh. Right, so,
Or it's no, you know.
well, I mean, you've always got the trivial valuation on any field, right? So I should have said what are the non-trivial ones? Right, the trivial valuation is you give everything value 0, right?
We're looking for the, yeah.
Okay, that's right. So taking inspiration from that, this is a quotient field with Z, and the fact that I know that there's a bunch of valuation domains, there actually is a valuation for every P. Let P, not 0, be a fixed prime. If you take your fixed prime to be 0, you'll get the trivial valuation. Now, this is a little bit trickier. Well, again, it's kind of easier when you see it, but given any element K in Q minus 0, I can write it as a fraction of 2 integers. Agreed? I think we can all agree on that, right? And I further. And do that. So what have I done? I've taken a random fraction. I pull all the P's out of the numerator that I can. I pull all the P's out of the denominator I can. And there could be as little as 0, right? No problem there. And basically I just jerk stuff out of this until what's left over is relatively prime. You got no more P's in it, right? Now, how does what value work here? I can now rewrite this as K equals P to the N A prime of B prime, where GCD A prime P equals GCD B prime P equals 1, and N is an integer, correct? So how am I going to work this valuation? Well, I'm going to take V of K, which is not 0, to be V of P to the N, A prime over B prime. I've convinced myself that every non-zero element can be written in this form. And in fact, it can be written in that form uniquely, right? If A and B are integers of relative prime. And I'm going to let that be N. And this is my VP from Q minus 0 into the integers. This is called p-adic valuation. Let's kind of go through this. If you look at B of P to the N, A prime, B prime, P to the M, C prime, D prime, where GCD of X prime P equals 1. So any prime letter that I use, I'm assuming is relatively prime to 1. Relatively prime to P. This is course, I can rewrite this way. And lucky me, because Z is a UFD, since A and C, A prime and C prime are relatively prime to C, so is A prime C prime. You can't pick up a P accidentally doing this. And this is, which is and if you look, using my same notation again, if you look at the valuation of, let's say, P to the N, A prime over B prime, plus P to the M, C prime over D prime. Well, what would you do here? Here again, we will assume that N is less than or equal to M without loss of generality. And basically, we do the same thing we did here. We pull the little guy out of the big one. It's P to the N, A prime, B prime, plus P to the M minus N, C prime over D prime. Now notice this is a fraction of two things relatively prime to P. This is P to a non-negative power. So how can I rewrite this fraction? This is P to the N times whatever this mess in here is. This is B prime, D prime. This is A prime, right? C prime, D prime. Right, remember that? Old two can still have fractions. I'm tempted to say, just as before, that this is valuation at the end, but I had the same problem that I did before. Let's look carefully at the numerator and denominator. Certainly the denominator is still relatively prime to P, no problem there. The numerator is problematic though. Again, if N minus M is positive, so if N is strictly less than M, then you get N here because the numerator, this has a factor of P in it, and you add it to something that has no factor of P in it, this is relatively prime to P, right? And so if this is actually a positive power of P, then you get what you want. Unit of relatively prime to P over relatively prime to P. The problem again becomes if N equals M, then that's a zero. And so even though A prime and B prime, C prime, A prime and D prime, C prime and B prime are relatively prime to P, when you add them up, you might pick up a factor of P. That's a possibility, right? 2 plus 3 is 5, right? And neither 2 nor 3 have a factor of 5 in it. It's possible to pick up more powers just adding to this. So it is at least N again. We could do another example. Here's one that we looked at before. This one is what's okay. Well, what's the part of this? Remember this one, this kind of monoid ring or group ring, or whatever, semi-group ring. These are just polynomials, F, but now I'm allowing the exponents to take place over any positive. R, quotient field K is all fractions from R. And earlier we had this valuation domain V. Y'all remember this one? And it turned out that R is the quotient field of this valuation domain. In V, every element are of form x to the gamma times x to the gamma comes a unit where gamma is here greater than or equal to 0. So your valuation, so in K, any element of K looks like any non-zero element of K then K is equal to x to beta u, where u is a unit in V and beta is any real number, positive or negative. And the value of x to beta times u is theta. You should verify for yourself. It's actually easier that this one is in fact valuation as well. So that one gives you a kind of a big valuation where you can this one here. Any questions? All right, we'll pick up more on this and I'll show you the connection between these valuation domains next.